wife, Robin, she teaches English for foreign students at Stanford University. So if you want to learn about how to write in English, talk to Robin.
All right, well, thanks for having me. It's a pleasure to be here. And so a little background. So again, Algo-Logic is algorithms and logic. And so that when I was doing my sabbatical at Stanford University is that we had a project doing software-defined networking, and what came out of what we were doing with this was called gateware-defined networking. And so the idea is, what if you use, instead of software, what if you use FPGAs and logic gates to make networks go faster? And what if you put them into the data center so that you can make systems that can compute more efficiently than you would typically do with a multi-core CPU? And so one of the projects that we applied the FPGAs to was something called a key value store. And so key value stores are used really commonly, like at Amazon, for example, the S3 store. Facebook, Google also uses key value store. Pretty much every data center application uses key value store because it's so easy. Is that if you want to associate and save a piece of data, you just assign a name to it, and you can write to it. And so we built a key value store in FPGAs, and then we applied it to an application of the scale-out machine learning with this FPGA key value store. And so that's what I'll talk about today. So the outline of this is that the system that we're talking about is this key value store that's implemented on an FPGA, and it lets you directly access data both from a CPU and from the network. And so from the CPU side, over the PCIe bus, you can read and write key value pairs, but also over Ethernet, you can read and write those key value pairs. And so anywhere on the host, you can have these associations of data values, and then anywhere on the network, you can also get to those as well. And then the benefit of doing it on the FPGA is that it can do this a bit faster. And so in a data center, you don't just have one system, but you have many systems. And so in this topology of having the FPGA connected to the CPU and the network, you can have a top-of-rack switch where you can scale out the configuration. And so in a data center like the Microsoft Azure, for example, is that the FPGA is in between the CPU and the top-of-rack switches. The top-of-rack switches is what connects all the computers in the data center. And so the benefit of this is that you can share data across all the machines with very low latency. It's just an Ethernet hop or two to go between an FPGA to another FPGA. And so the application that we have is, given that we have this topology of being able to connect multiple FPGAs to multiple CPUs in a data center, is that how can we drive this with an application? And so the application that we applied this to was self-driving cars. And in particular, we used the machine learning model called a Markov Decision Process. And so through this, what we show is that we can teach cars how to drive on a highway. And it turns out a couple of compute clusters and a couple of FPGAs can make this learning process happen in minutes. And we can also use not only for the learning process, but it's a continuous learning process. And so once we've taught the machines how to learn, we can also use them to actually drive the car. And so what we have here is a simulated cars, but you can also, because it's real time, and you know how long it takes for it to respond, is that you can also use this for actually driving a real car. So first, a little background on the key value store. Again, it's just an association of data with names. And these names can be anything. They can be telephone numbers, they can be graph edges, they can be vertices, they can be address, they can be geolocations, they can be graph edges. The data can be coming from things like sensors, like the location, a GPS coordinate, for example, things that move, like an accelerometer. It could be social status, like in Facebook. Key value stores are to keep track of your status. You know, are you married, single, something in between. Is that real-time games use key value stores as a way to share data. And telco networks is that as you're doing things like handing off between base stations, is that you may want to have key value stores as a way to keep track of what node your call is on. And then for databases, keeping track of users, payments, authentication. There's just all sorts of use cases for this key value store. And so, and the key value store, in the case that we have here, is that it's how do you make an architecture that can provide the best latency, throughput, and power. So it's fast to respond, handles a lot of transactions per second, and it doesn't use much power. And how can you make it so you can scale out so that you can deploy a lot of these and get more throughput and more redundancy? And we did this by putting this in FPGA logic, connecting it to Ethernet. So this supports this fast in-memory storage so that you can build cloud services that share data with the key value stores. You can build parallel file systems so that if you have things like the distributed asynchronous object store, DAOS, which is part of outcome of Lustre, is that you could build potentially parallel file systems with underlying key value stores. And to make it usable for software developers, have a fully open source API so that as you create, read, update, and delete these key value pairs, you can do this from any software program, a C program, C++, Java, etc. So the servers that this goes into is a standard rack mount server. And so, for example, an Intel CPU and an FPGA on a PCI Express card. So this is a one-use server, very common in data centers. And the application for this key value store is just something that runs on the FPGA. And so in the network architecture is that as you have lots of, say, IoT devices, and you've got things that are making decisions, is that you have this topology of having these devices out in the real world or out in the internet that are pulling in data, smart cities, cars, whatever, is that you have all these internet-attached devices that are sending data to things that need to make decisions, but also they're sending data to the cloud. And so as it goes into the cloud, you have the scale-out compute systems where you can do things like machine learning at scale. And you can use GPUs, CPUs, PHY processors, neural net processors in the data center. And then you have attached to the compute nodes is memory. So you've got in-memory SRAM and DRAM and NVMe so that you have this parallel system that can be computing and learning based on real data that's coming in. And then after you've learned how to do something, you can push that result out to your decision-making process. So now your decision-making process has inputs coming from what was learned in the data center, plus the real-time inputs coming from the IoT devices. So a little bit about machine learning, the Markov Decision Process. So this is Stanford University has a class on Markov Decision Processes. That's an AI class. And we use material from that class as the basis for this application. And what we changed, though, is that instead of having the data stored all in software, is that we used our key value store to store the state value and the actions to take, and also the policies that the MDP would take. And so the Markov update server is, we're updating the Markov model, and we have the states, and these actions are what to do to go from one state to the next state, what the actions are. And so we have tables that are stored as key value pairs, and ultimately you're coming up with a policy, which is from a given state, what's the best decision to make on what to do next. And so then you can make that decision, you can apply that action, and run a simulation to see what did that action do? What was the outcome of doing that decision? And then you can record those outcomes back to the Markov model, and then you can iterate through this process of coming up with the states, simulating the action of being in the states, looking at the outcomes, and then repeating. And if you repeat this for a while, you end up coming up with a system that learns how to do something. And so in this case, we were looking at the problem of self-driving cars. And so, and again, a scaled down version of a self-driving car is that it has some system state. So that system state of this car is it has some velocity that it's going. It's got some distance to the car in front of it. And it's got a change in the distance of how far it's converging to the car. It has inputs from sensors that tell if other things are nearby. So if there's something left, right, bottom left. And so, of course, in general, you've got more sensors than this in most cars. Is you have cameras, you have LiDAR, you have ultrasound, you've got a slew of sensors. But no matter how many sensors you have, is that you need to discretize that data down to a finite state set. And so the state set is enumerating all the possible states that your car could be in. And you have to make some approximations. You said you need to round. It doesn't matter exactly what velocity, if you're going 70 miles an hour, 71 miles an hour. To the car, that's pretty similar. Ultimately, you need to come down to discrete states to make this mappable into a Markov model. And so these are some of the relevant parameters that we started with as the first approximation of the self-driving car. And then for the actions, is that what do you do given the states that you're in? And so kind of actions would be to coast, just keep going the same speed you're going. You could accelerate by pressing the gas. You could brake to slow down. You can merge left or merge right. And so for typical highway driving, these are the decisions that your car would have to make in order to stay on the highway. So now let's talk about a Markov model. And so a Markov model is like a big state machine. And over time, the state machine moves from state to state. And it spends a different amount of time in each of the states. And so we can set the probability of going from a state, given the state in an action, moving to the next state. So that's what we're showing here, is that we have the Markov model. The probability is the probability of going from this state to this state, given some action. And so for all the possible actions in all the states, we have all these variables that we want to keep track of. So we have the state, the action, and the next state. And this Markov model is this gigantic state machine that will fill pretty much as much space as we have available based on how much we discretize the states. But the key point here is that the Markov model is continually bouncing between states as you spend a certain amount of time in a state and then make transitions to other states. And it's not just along a line, but it's along all the possible dimensions you could go in. And so,
how do you connect the states to each other on a conceptual level? Because some of them will be dependent on each other.
Right. Right. So the key values, so the actions from state to state. So this is the keys in this table are all possible states, all possible next states, and then this is the probability of making that transition. I'll connect the probability to the times that we spend in states in minutes. That's kind of the key feature that this Markov learning model takes advantage of. Is that it turns out that the time that you spend in the state in steady state is proportional to the probability that you're going to be jumping between states. And that's the solution that we're looking for, is this. But this is the states we have. And so there's a lot of states because for all possible discretized states and next possible states, we have this big matrix. And all the actions are what we do in each of these states.
When you build this, do you feel that it relates to your own actions when you are driving your car? How much does it model? How much when you model it, does it like intuitively match for you?
Right. So we start out. So I'll show when we build this car on the road at first is that it has no notion of how to drive. And so that none of the states that we're going to show you are learned.
Okay. And
so all the learning that it does, it picks up on its own by running through these simulations. And so there is no programmed intuition, which is your question, is that we didn't program anything to the car about how to drive, but we just gave it a framework, which was how to model the states that a self-driving car could be in. And so talk about the actions, the states. So the key feature, maybe not intuitive, but the part that makes all this work is that if you run a simulation of a system that works and you keep track of how much time that you spend in certain states, that's time, you can make that proportional to the probability of going between states. And so this kind of connecting feature is that the time that a system in steady state spends in a state can be made proportional to the probability that you should jump to another state. And so that's the magic of the Markov decision process as learning. And so now you can set reward values, and so the certain states are good states. And so you can associate a positive reward when you get into a good state. Having an accident, for example, is a bad state. If you run into another car, that's a very negative outcome. And so you definitely want to avoid getting yourself into a state where you have an accident. Now, you can also work backwards from that, is that given that a state, typically a car accident happens when you're accelerating up to a car in front of you, you hit it. So that end state of hitting the car has a negative reward function, but also the states that led up to it. When you're accelerating and the car is near in front of you, you can associate that. Working backwards, you can also find that that state, you can put a discounted rate for future states. And so when you're 5 states away from having an accident, is that you can associate a discount rate for the future. And so y squared q fourth is that, so the subsequent expected rewards, you have the immediate reward of not having the accident plus the future value of states that lead to the accident. And you can have increasing weights as you get closer to that state. And so this is now getting into how the system, how the computer has an idea of what's good and what's bad. All it knows is that having an accident is bad, but things that lead up to having an accident a few states away are also bad. And intuitively that makes sense because it's the car that runs into another car. It wasn't just the fact that it happened in that last state. It's the fact that it was accelerating, or the two cars were on a course to collision. And so this is how you can model that. As you become close in state space to a negative outcome, that you can have a weight that factors that. So the goal then is to choose actions, have the system choose actions that maximize the expected future reward. And so you have an immediate reward. If you have an accident, for example, that's a negative reward immediately. You have the future value of the expected reward of going to that state, this discount rate that considers how far in the future you're looking. And the idea is to choose an action which maximizes the best future reward. And so if you take the action and you choose the best action such that the probability of going from making a state transition from state S prime to S, and you make that action, you look at the reward that you're going to get from that next state and the subsequent future value of the other states that lead up to it, and you sum that up, is that you can come up with a decision about what is the best thing to do given the states that you're in, what state will give you the best next outcome. And that's leads into the training. And so to do this is that we can start with initializing the value of future rewards, and we go through this loop of convergence. And so we're picking the next best possible action from some state transition reward, and we're finding the best possible future value by looking at the reward state, choosing which action to take that gets us to the best future. Okay, so what does this look like? And so, so this is the dashboard for the simulator. So now at this point, we've taken the highway, we've created a visualization for the self-driving cars where that we have we're simplifying the problem of driving on a highway. And so in this case, we have 30 instances of the self-driving car we randomly throw out onto a highway. And each car is initialized with a different initial velocity. So like cruise control. Every car is given a different speed that it's trying to go at. And that as these cars navigate down the highway, because they're going different speeds, they have to find a way to weave their way through traffic. Which means they have to know what to do as they approach other cars, know when to change lanes, and know how to get there. And they start off knowing nothing. And so this dashboard is just simply a Chrome browser where it's just rendering, a vanishing point in the future, and it's placing 30 instances of our self-driving cars. They're all equal cars. It's a fleet of cars that are all running the same algorithm. And all of these cars are making decisions on how to move through this world where they're applying the Markov Decision Process to make those choices. And we're looking at the average time without an accident. So if we start out, and we'll have a video on this in a minute, is that where at time equals 0, when we first fire up the simulation, it's like bumper cars. These cars are running into each other all the time. And so, but they're learning, is that every time they do that, that simulation ends with a negative outcome. And so we know that we need to weight those states that led to that accident in a negative way. And as this runs, and these are seconds, and over time, we can go longer and longer without having an accident. Now sometimes there's local minima and maxima here, but overall the trend is the longer the simulation runs and the more interaction that these cars have, the longer they go without having any accidents, until the point where they go a long time without having accidents. And so this generates a bunch of burst or key value stories. I mentioned our key value store is keeping track of all of the states, the action tables, and so all the data that's being shared in the system is coming back to the key value store as the place to put it. And we did this first with just one thread running at real time, where what you'll see on the screen is running at normal speed. But in order to train faster on a parallel computing system is that you want to run a bunch of parallel simulations. And the nice thing about running simulations is you don't have to be limited to real time. You can run as fast as your simulation will let you run. And so in the system that we're running, as I mentioned, the scale outside of this is you can take a multi-core system, and on every core, you can run a simulation. And one of the simulations is the real time that we'll see on the screen, but all the rest of the cores are running simulations that as fast as the CPU can run, which is about 10 times faster than real time. And so then we have all of the cores running in parallel, and so we end up having hundreds and thousands of simulations that get run. And so it's kind of akin to driving school, is that we take our system out and we let it drive, and that it turns age 16 and then it goes on the highway, and it usually takes a human driver months to a year or so before they're kind of comfortable driving on speed. And in this system, the system is able to run a bunch of parallel computes at faster than human speed, and then with many instances running, sharing the results back to the key value store. And it turns out they can run in minutes. And so I'll show that.
Quick question.
Yeah.
Do the vehicles not know anything about each other's system states?
So the vehicles, what the vehicles know is that every vehicle has access to those states about the sensors of which cars are nearby them.
Right,
How
but
far?
they don't have the individual state of each vehicle as knowledge to each other. Like say a vehicle within the vicinity shares the system state with another vehicle.
Right. So through the key value store, each car is accessing state, the